So, today's lecture is open ocean. So, we are discussing the first part and we are discussing what is happening to insolation or light and heat. Now, first we will discuss about light. So, light consists of various wavelengths and let us have a look what is happening to this. So, on this scale you have wavelengths in centimeters, wavelengths are given in centimeters. Now, you split it up into number of regions. So, this is from 10 to the power minus 11 centimeters to 10 to the power minus 14. So, this we are discussing light. So, these consist of mainly cosmic rays, or you can write gamma rays. Now, still going down, we have larger wavelengths up to 10 to the power minus 6, you will get X rays. Then is ultraviolet radiation. UV stands for ultraviolet radiation, that will go up to 10 to the power minus 4. Below that you have visible light. Still increasing in wavelength, you have infrared. So, this is up to 10 to the power minus 1 centimeters. Then you have microwaves. Ten square. And below you have radio waves, electric current. So, this is your wavelength distribution of the light, which is coming in the form of all these rays. Now, light itself, the visible portion itself is split up into still further wavelengths. So, you have violet, then indigo, then blue, green, in short VIBGYOR, yellow, orange, red. And below this you have the infrared radiation. Now, last class I told you that this blue wavelength is more reflected. That is why C looks blue. It is not absorbed. Now, this infrared, it is quickly absorbed. So, this causes the ocean surface to be heated up. So, this is quickly absorbed. Within, of course, 1 meters. Within 1 meters from ocean surface. So, all this is actually used by your satellite in order to map the heat and the color of the ocean. So, after this, the visible part, now visible part is also absorbed, changed to heat. And all visible light is absorbed in 100 meters of ocean depth from surface. So, below 100 meters you will find pitch dark. Now, this process of insolation is the process of absorbing heat from the sun by the ocean. This is used by plants in photosynthesis. So, now let us have a look at the solar radiation that is affecting the ocean surface. So, this is your earth. Now, the earth is actually spinning about its axis and the axis is somewhat inclined. The earth is also flatter at the equator. So, this is your equator. So, it is rotating in this direction, this is north, the other is the south. So, obviously, if your solar radiation is from the left, then this portion is day and this portion is night, that is part which is not affected by the sun. So, night is the absence of solar radiation. Now, if you make a energy sort of, if you look at the latitude of the earth, you have to make what is called an energy audit. Now, energy received from sun, at top of atmosphere. So, this is 0.5 calories per centimeter square per minute. Now, part of this energy is absorbed by the atmosphere or stratosphere. So, at the earth's surface you have only 0.25 calories. So, energy received at earth's surface So, this is only half. So, 0.25 calories per centimeter square per minute. Now, this is on 24 hours basis. Now, if you look at the surface of the earth from the equator to the poles, you have the distribution like this. So, this is the equator at 0 degree. Somewhere around here you have 30 degree latitude, then you have 50 degree, and right here this is 80 and this is 90 degree. So, this is your equator and this is your pole, say north pole, if you are doing for the northern hemisphere. Now, if you plot this, the radiation or solar radiation you can call it. So, this is given in calories per centimeter square. Now, the unit is calories per cent, this is in days, right. The previous one I have written in minutes. So, this you will find this start, this is somewhere you have 100 is the minimum. Then use 450 is there, and this is 600. Now, your insolation graph will go like this. From 600 it will start at the equator, this will come to, obviously this is not a straight line, it will come to 100 at the, this is 100 at the poles, say this is north pole. So, what is happening? So, this is your insolation. Now, there is another graph that I have drawn, this dashed line, this is called outgoing radiation. So, insolation is incoming radiation, that is you are absorbing heat from the sun, and outgoing is that which is going out. So, in this region where insolation is greater than your outgoing radiation, and this should occur somewhere around 30 degrees. So, from my graph it is coming more. So, you have surplus, and in this region you have a deficit. And this will normally occur in this region, that is subpolar and polar areas. This is subpolar and polar regions. So, here actually the heat loss is more, that is why this region is cold. So, this region must be away from the sun. and that which is nearest to the sun you have insolation. So, this is tropics and subtropics. So, in our region actually we are fortunate in having a large amount of solar radiation, which of course, if you put into good use, it will be your benefit.
So, up to how much from the equator is the surplus?
So, surplus is going according to this graph, actually I have drawn it around 50, but this should be falling somewhere around say 40 or 45 degree, this point. So, this is your insolation graph. Now, after this what you do is the heat balance or heat audit. Heat balance at ocean surface. Now, this is done on a 24-hour average. So, if you want to do a heat audit, so that means you should have two columns. One is for heating or cooling, the other column should be cooling. So, you do the heat balance. Now, the units are in calories per centimeter square per minute. So, in first one is incoming solar radiation. So, how much that is coming to the ocean surface? I just now told you. So, incoming solar radiation from my previous lecture, it is only 0.25, isn't it? So, that is coming to the ocean surface. Now, how it is getting distributed? So, radiation back to space. Radiation back to space is only 0.10. Obviously, back to space is causing cooling. 0.10 is going out from 0.25. Then, what are the other mechanisms for heat loss? The other one is evaporation. So, that is also 0.13. Atmospheric warming. So, this is by conduction. So, this is another 0.02. So, now you have got the heat balance. So, that means the earth surface is receiving 0.25 and it is consuming also, you add up you will get 0.25. So, this is the heat distribution. So, the conclusion is ocean loses as much energy as it absorbs. So, this is what is happening at the ocean surface. So, this atmospheric warming is the cause of the wind circulation. Now, because of this you have what is called, because of insolation you have a temperature what else, salinity and density gradient in the ocean. Now, if you look at the chart, you will find your temperature. Now, this is affecting the surface waters most. Up to what depth? So, if you make a chart, you find your temperature is varying in this manner. Salinity is the opposite. More or less the same is your density incline, but is more sharper. So, temperature is increasing in this direction. This is centigrade. Salinity is also increasing. Now, salinity is expressed in parts per thousand. So, you write in this, and the last one is your density gradient. Is in grams per centimeter cube. And this is affecting from 0 to 4 kilometers. So, depth of ocean. Depth you take 4 kilometers. So, around this you will get 2, this is 1 and this is 3. Now, you tell me which are the zones. So, this is your, this is the surface zone. This is the surface zone. Now, below this you have, now you have sharp changes in density. So, this is called, also associated temperature is also varying to a large extent. Variation of all the three quantities are quite large. So, this is the pycnocline. And below it you have the deep zone. So, deep zone there is not much change in the three parameters, you can see more or less constant. So, the first one is called a thermocline. The oceanography books you will find these three diagrams. Change in salinity is called a halocline. The last one is, of course, you know, Pike-Noak line. So, these are the three inclines or the three graphs depicting changes in temperature, salinity and density. Now, your salinity, this is the main cause for change in the density of the ocean. Now, its variation you can see from the graph. Now, please do not talk, this is being recorded. Salinity, you have it increases from 30 to 40. Now, most of the ocean waters lie around 35 parts per thousand salinity. Temperature variation, of course, here it is quite large. So, I told you it is stretching in this graph. You can see from 0 degree at the ocean depths to 30 degrees centigrade at the ocean surface. So, here you have 10, this is 20. Now, around this 30 you have the ocean surface. So, this is 75% of ocean surface waters. Or rather you write ocean waters. Now, this actually 10 will be slightly above this. Here you can write 10. And the maximum ocean waters will be having this kind of distribution. So, this is 99% of ocean waters. Now, if you look at this diagram, the larger one, so average temperature is only 18 degrees centigrade. So, this is your surface waters. Surface water temperature, average temperature, you can take it as 18 degrees centigrade. And the other one is your deep water. Average temperature is only 3.5. Average salinity. So, from this diagram, how much is average salinity? 34.7 parts per thousand. So, this is your distribution of temperature and salinity in the ocean waters. Now, salinity changes. What are the cause of these salinity changes? Now, salinity change is another cause for a density change. So, both are linked. So, salinity changes are caused by number one, you write evaporation. So, this is the process of removal of fresh water. In short, I am writing FW as water vapor. What is the other process? Number two is precipitation. So, this is the process of adding fresh water or adding of fresh water as what? As rain, snow. The last process is number three is river discharge. So, this also there is addition of fresh water. So, these are the three primary causes of salinity changes in the ocean. Now, if you look at evaporation, this is maximum in subtropics. Subtropical regions from, you write in brackets, I am writing 30 degrees north to and 30 degrees south. Why? Because of this region is getting affected by maximum by solar radiation. Now, as a result of this, you have trade winds. So, this is happening at 30 degrees north and 30 degrees south latitudes, blow throughout the year. Now, trade winds, they are being called trade winds because they are able to move ships throughout the year. You write high insolation. Now, high insolation you can only have if you have clear skies. So, this region is not marked by cloudiness. Now, as a result of evaporation, you have at this region you will have high surface salinity. So, that means fresh water is being vaporized. So, what is remaining is the salt in the ocean, that is a cause of high surface salinity. Now, in our case where we are situated near the equator, we have precipitation. This is most abundant near equator. high latitudes. High latitudes is greater than your 30° north and south, and coastal regions. So, what is happening here? Lower evaporation. In equatorial region. Due to light and variable winds. So, this is called doldrums. And the other cause is cloudiness. This is reduced insolation. So, in this region what you will have? You have precipitation means more rainfall. So, the equatorial region is affected by more rains because of this kind of activity that is taken place, lower evaporation. Now, after this we come to surface current. So, what is the cause of surface currents? Or main driver is of surface currents. Because of winds. So, if you want to study current, you have to know the wind pattern. Now, this pattern, or rather you have basic pattern. Basic pattern of open ocean current. This is called a gyre, G-Y-R-E. The pattern is called a gyre. Now, what is a gyre? This is a closed loop or a circle, or rather best you write this as closed loop. I will draw the diagram where you can see this. This is called a current gyre. So, each ocean has a current gyre. Each ocean has a current gyre. This is centered. So, it will be something like a ellipse more looks like a ellipse centered in subtropical regions. So, subtropical regions you write 30 degrees north and 30 degrees south. (30° north and 30° south latitudes). This occurs at of each hemisphere. So, this is a current gyre. Smaller gyres occur in subpolar oceans. Or rather you write subpolar regions. So, this is located near 50° north. North Atlantic Pacific. Now, if you have a look at this current gyre, you can see in this, because current gyres actually influence the direction of the wind. So, if you draw two diagrams, one for the wind distribution and the other is the current distribution, it will look like this. So, this is your land mass. So, this is occurring between the boundaries of, so as an example you can say this is the Atlantic Ocean. So, on both sides it has been bounded by the land mass. This is land, this region is also land. Now, you have a current at this region. So, this is called EC or equatorial counter current. Now, on top of this I told you at 30 degrees you have centered around, this is 0° latitude. So, your equator is at 0° latitude. Now, you have the 30° latitude. So, it is coming somewhere here and on top is your 60° latitude and of course, at the top is 90°. So, this is the northern hemisphere. So, this is 90° at the poles, north pole and right end. Now, if you look at the current distribution around 30°, it has been said that you have a current gyre. Now, you tell me in which direction this will go. So, gyre is a closed loop of water. So, it is circulating in this manner. So, direction is clockwise, and why it is clockwise I will tell you. And on top of this you have, as has been said, around 50° north you have another current gyre, but this direction is opposite to the one which I have drawn. sorry, this is clockwise and this is going in the anti-clockwise direction. Yeah. Sorry, yeah. So this is subtropical gyre. And on top of this you have the subpolar. Now what is happening at the southern hemisphere? So this is called the northeast or north equatorial counter, and down below you have the reverse. So which direction this will rotate? This is called subtropical gyre. Now here there is one remarkable, near this is your south pole, or 90 degrees south. Now 90 degrees south you do not have the subpolar gyre. Have you noticed? The subpolar gyre is absent, but here you have a huge mass of water drifting around the globe because there is no land mass. So this is called, since it is coming from the west, this is called west wind drift. This is called west wind drift. That is the coast of Antarctica. It is more or less unaffected by your land mass. But in the northern hemisphere, you have more land mass. So that is why you are having this gyre. So NE stands for North Equatorial Current. SE stands for South Equatorial. And EC is Equatorial Counter Current. Now, if you happen to have a look at the wind distribution, it will be like this. This is 0 degree latitude, or you have 30 degrees and 60 degrees, let us say, out here. Now, if you want us to study the dynamics of the ocean, you have to study everything in totality, that is your current plus wind, etc. So, which is of course not a very easy job. So, south you have this 30 degrees and this is 60 degrees. Now, here actually you have the wind pattern. Sorry, 60 degrees here. The wind is coming from this direction. And near the pole it is coming the reverse direction. Now, what is the cause of this wind? So, heat. So, these are called westerlies. Now, actually, oceanography started from study of the wind pattern and current. So, that is our forefathers, they studied all these wind patterns and current for trading, that is the ship, finding the favorable ship routes. Now, in this region, this is coming from the east and the north. So, these are called northeast. Anyway, so this is coming from the north. These are called northeast trade winds. This is your northeast trade winds. That is, the ships, they used to trade in these routes. So, they are called northeast trade winds. Now, in the opposite direction, you will have the southeast trade winds. So, that is coming in this direction. Now, nowadays you are not having any sailing ships, you have powered vessels. But what is the use of this wind distribution now? So, these are called southeast trade winds. Now, in between the northeast trade wind and southeast trade winds, you have a region of no wind. So, these are called doldrums. And again, below the southeast trade winds, you have winds coming from the west. So, these are called westerlies. So, this is your earth wind pattern. So, this brings us to the end of Open Ocean 1. Next, we will have Open Ocean 2. We will discuss Coriolis effect and the Ekman spiral. So, you can have a short break, but you come after say another 5 minutes.